Okay, so before we look at the next lesson, there is one question we didn't finish from the last one, and that is a mixture problem. Okay, so let's just look at this. This is very similar to question 48 that I had you guys skip in the homework. It just has different numbers. So if you had 50 ounces of a liquid in front of you, okay, let's say the volume of the container in front of you is full of 50 ounces of liquid, and I said to you 35% of the liquid in front of you is acid, and the rest of it is diluted with maybe water. How would you figure out of the 50 ounces, how many of the ounces are actually acid if only 35% of what you have is acid? Yep?
Wouldn't you figure out what 35% of 50 is?
Yeah. Okay. So if you had 50 ounces of liquid in front of you, and I said 35% of what you're looking at is acid, the other 65% is water, you would have to find 35% of 50, which means 17 and a half out of the 50 ounces is actually acid in the solution. Okay. Any question on that? That's the first part. What they're going to ask us to do is find a concentration. Okay, so if you're not sure what that means, concentration is pretty much the same idea as like calculating your score on a test. Okay? Like when I give you a grade on the test, I calculate the concentration of how many problems you got right. It's basically what I'm doing if you word it that way. So if you had 20 questions on the test and you got 17 right, I take the concentration or the amount you got right, 17, and I divide by the total, 20. So you got 17 out of 20. And if I convert that to a percent, that's 85 or 0.85%. We're doing the same thing here, except it's not how many questions you got right out of the total number of questions. It's how much acid is there out of the total volume of liquid. But it's the same thing. A concentration or a percentage is always the part you're interested in divided by the whole, or the total. Okay? So that's how you find concentration. This will give you an answer between 0 and 1. If you wanted to make it a percent, you'd have to multiply it by 100. So like this will give you an answer like 0.37. That's 37% if you multiply by 100. But that's always going to be between 0 and 1. I don't multiply by 100. I just leave it like that. So we're going to take that solution that we had, 50 ounces of liquid, 35% of it is acid, and we're going to pour 100% pure acid into what we already have. So what we're doing is we are making it stronger. They want us to find a graph of the new concentration. Now, we're going to be adding X ounces. That's how much acid we're going to pour in. So there's no limit. You could pour in 1,000 ounces if you wanted. Okay. Let's write a formula for the concentration. I'm going to name my function C, because C stands for concentration. And it's going to be the concentration as a function of how much acid I pour in, X. Okay. What goes in the top when you're finding your concentration in this problem? Yeah?
The total acid.
the total amount of acid. Okay. There's two sources of acid. We started with some and we poured some in. How much did we start with? Yep.
35%.
So it has to be an amount of acid, not a percentage of acid.
17.5 ounces.
Yes. We started with 17.5 ounces. And how much acid did we pour in? X. That'll be the new amount of acid that you have. What you started with plus what you poured in. And when you find concentration, what goes in the bottom? Total amount of liquid. How much liquid did we start with?
50.
Started with 50. And how much liquid are we adding? X. That is your new concentration. So let's graph that. Can the concentration ever reach 100% if we keep pouring in more acid?
Yeah. No.
Why? Yeah.
Because it never started at 100.
Never started at 100, right? It's like if you had a bucket of white paint and you put a drop of red in it. It's never white again, right? You can keep pouring white in, and it'll be like 99% white paint and like really small percent of red paint, but you can never get it back to white paint. It still has something in it that's not white. So same thing here. You still have something that you started with that wasn't acid in the beginning, so no matter how much you pour in, it'll never be acid, 100%. So let's graph it. 17.5 plus X divided by 50 plus X. Can we pour in a negative amount of acid? No. We can pour in as much as we want. And the concentration, what did I say this always comes out between? 0 and 1. Unless you multiply by 100, then you get 0 to 100. It's going to be between 0, which represents no acid, and 1, which represents 100% acid. There's the graph of your concentration. So the more acid you pour in, the higher the concentration gets. But it can't reach 100. It can get close to it. Because it can't reach it, mathematically, what does that mean we have at y equals 1? Yep.
Horizontal acid.
Yeah, there's a horizontal asymptote. We can't ever reach 100%. They want us to figure out how much acid would you have to pour in to make the concentration of the acid 75%. So right now it's at 35. I want to know how much I need to pour in to get it up to 75. Okay. How do you think I'd use my graph to do that? Yeah? Yeah?
Separate question.
Yeah.
If you were calculating the mixture of like the water in it instead of acid, would there be a horizontal asymptote of 0?
So if you were calculating the amount of water in it, yeah, I guess that can continue to get lower and lower and lower and lower, but it would never reach 0 because there's always acid in it if you were pouring water into it. Yeah, it could never reach 0, but it could approach 0 for the amount of, like, the concentration of that. You're talking about like the concentration of the acid?
The
Like if you were to-
concentration of water, if you kept adding acid, it would keep reaching 0, right? Water concentration.
Oh yeah, the concentration of the water would, yeah, it would get closer to 0 because the acid would get closer to 100. Yeah. Yeah. So what do we have to put in Y2 to see when we reach 75%? Yeah?
0.75.
0.75, yeah, not 75, 0.75. Okay, so there's where we reach 75%. And what do we have to find now? Yeah, we just have to find the intersect. So if you pour in 80 ounces, you will get a concentration that's exactly 75%. So this kind of question would have two parts on the test. Okay, the first part would be to write the concentration formula. And then the second part would be to find an intersect and write down the amount. Any questions on that? Okay. All right, so now we're going to take a look at 4.2, which we'll split into two parts. We've started looking at rational functions. Talked a little bit yesterday about asymptotes, horizontals, and verticals. And now we're going to use those today to draw sketches. Okay, so most of, I think actually everything we do today will be a sketch. Now, one thing we do have to remember, when you have a rational function, if you have something like this, what value would cause you to divide by 0? 3, yeah. 3 is an undefined value. Would it be an asymptote in this graph, or would it be a hole? Yep, this would be a hole. Because remember, when you have a common factor in the top and the bottom, that's the hole in the graph. You can't see it on the calculator. What's the other option? If you divide by 0 and it's not a hole, then the other thing it could be is a, what kind of asymptote?
Vertical?
Vertical, yeah.
That's a difference.
So if you don't have any common factors, then the zeros of the denominator will be your vertical asymptotes. If you do have a common factor, that's a hole. Okay, so that's just a reminder from yesterday. Let's think about this one before we graph it. F of x equals x minus 1 over x minus 1. Is there a value you could plug in for x that would cause you to divide by 0?
1.
Yeah, 1. So let's try it. X minus 1 divided by x minus 1. Let's go to the table. Type in 1. All right, definitely that's an error. You can't plug in 1. Would we have a hole in the graph at 1? Or a vertical asymptote?
Hole.
A hole. So when we graph it, let's do zoom 6. It's not going to look like anything happens at 1 at all. Can't even tell. Let me just, maybe if I add in something else. Up at 12, let's see. Well, we'll just look at that graph. Pretend that's that. There is a hole in the graph at 1. Okay, so when you draw it, this is how you would show the hole in the graph, if I could show it. Okay? Now, what if I did this? Let's just change this from a minus 1 to a minus 2. Is there a number now that would cause you to divide by 0?
Mm-hmm.
Yep, what number?
1.
Still 1. I didn't change that. Still can't plug in 1. But when we graph it, would you have a hole or would you have an asymptote at 1? You'd have a vertical asymptote because you don't have a common factor anymore. So it's going to start the same, but watch when you get to 1. Big difference. Really likes that graph. Okay. But that's it. Okay, so this one has an asymptote. I'm not going to graph this next one. But is there a value for this one that would cause you to divide by 0? 1. And would it be a hole or an asymptote? This would still be a hole, because this is just 2 copies of the same thing in the top. I Think of the top like that. So yeah, there's definitely a common factor again. It happens, there's two of them at the top. You don't need two to make a hole, you just need one. But it still would be a hole in the graph. All right, so when there is no vertical asymptote, another name for that is called a removable discontinuity. That's the fancy name for having a hole in a graph. Discontinuity means it's disconnected. It's like you'd have to lift your pencil up and put it back down to continue. And that's just a fancy name for having a hole in a graph. So now if I ask you on the test, does the following graph have a removable discontinuity? That just means, does it have a hole in it? All right, so when we graph a polynomial, you're going to have a problem like this. I've tried to represent that generically by that. This just represents some polynomial in the top and some other polynomial in the bottom. That's all they are. Usually when you write a polynomial, you start with the highest exponent, and the exponent goes down each time until you get all the way down to something that doesn't even have a letter in it, and that's your constant. Like this. We have an exponent of a 3, then it goes down to a 1, then we don't even have a letter. We're down to a constant. You don't have to have every power from the highest to the lowest. Like I have the 3, I have a 1. I don't have x squared in the bottom. That's fine. But that's the general idea. Some kind of polynomial in the top, some kind of polynomial in the bottom. When we talk about the end behavior model, which term in the top would have the highest exponent? Yeah, the first one. All the other exponents are smaller than the first one. That's the EBM of the top. Okay? So we talked a little bit, I think, about EBM in chapter 3, end behavior model. The end behavior model is just the highest degree term. So that's the EBM for the top. What would the EBM for the bottom be? Yep.
The BX.
Yeah, it would be the first term right here. That's the term with the highest exponent. All the other terms are lower degrees. So when you have a rational function, you still follow the same rules to find the EBM. Find the EBM of the top, find the EBM of the bottom, but then the answer of the EBM of the whole thing is when you divide the two. So the EBM of our rational function is the EBM of the top divided by the EBM of the bottom. And when you divide, okay, these two things are just going to be numbers. So if they reduce, we'll reduce it. If not, like if it was 2 and over 3, we just leave it as 2/3. But what happens when you divide two things that have the same letter for the base? Does anyone remember what you do with your exponents? That's when you multiply with the same base. You subtract them. Yeah. Okay, so when you simplify your final answer for the EBM, you're going to divide these two numbers, whatever they are, and then you're going to have an x, and the exponent is going to be n minus m, because that's how you find your exponent when you do division. You subtract. And that's the EBM for your entire problem. Now, if m was bigger than n, you could end up with a negative number for the exponent. We don't generally want to leave something with a negative exponent. If you add something with a negative exponent, where can you put it in a fraction so that it's no longer negative? If if you had something like this, how could I write that so there is no negative exponent? Yep.
X over 2. X squared. 1 over x squared.
1 over x squared, yes. So if you've got a negative exponent, we're going to put it in the bottom of a fraction, so that way it's not negative. So you can do this for like the first step, if that helps you to figure out the exponent. But if it comes out negative, we don't want to leave the negative exponent. Any questions on that? All right, so let's try to find an EDM for this one. All right, so we've got 2x to the squared, 2x squared minus 1, and 3x cubed plus 2x plus 1 in the bottom. What is the highest degree term in the top?
2x squared.
Yep, 2x squared. So we've got that. What's the highest degree term in the bottom?
3x cubed.
3x cubed. So we have 2x squared divided by 3x cubed. That's how we're going to find the EDM. We have to simplify. That's not done. Well, let's simplify. I have x squared in the top, x cubed in the bottom. When I'm done, I'm going to be left with an x where? In the top or in the bottom?
Bottom.
We're going to be left with an x in the bottom. Because if you subtract your exponents, 2 minus 3 is negative 1. X to the negative 1 means it should stay in the bottom. If you get stuck, I guess you could think of it this way. Two x's in the top, 3 x's in the bottom. 2 in the top, cancel 2 in the bottom. And what are you left with for final answer? 2 over 3x, yes. That is called the EDM, and that's how you write it. It's just a single term. There's no equal sign with it. 2 divided by 3x. That's the EDM. Now, let me graph it, and let's see what it looks like. Okay, I'll graph the original, and I'll graph the EDM.
What was the name for the highest term in the equation?
The term with the
2x
highest
squared.
degree.
Yeah.
Well, we usually put it first, and if it's first, it's called the leading term. Yeah. And then 3x cubed plus 2x plus 1. Okay, so 2 divided by 3x. What's that called again? End behavior model. End means not middle, it means on the ends, okay, like the left and the right edges. So let's do zoom 6. And let's see how this looks. Okay, that's the problem that I gave you.
The 2x squared minus 1 divided by.
And let me make sure I typed all that in right. I don't think I did. Nope, I forgot a parenthesis. When you type it in, you do have to put the 3x in parentheses. I didn't, and that's why it didn't look right. So that's the original, the f of x. And here's 2 over 3x. So I want to take that. I really do want to take that. I want that. So there's my graph. And I don't want you to focus on the middle. Okay, I want you to focus on what's happening on the edges. So I'm going to kind of just block the middle off. And just look at the edges. Okay, it's a little hard to see. The blue one is still there. It's like right underneath it, and it's right there too. How do those two graphs look, the blue one and the red one?
Aligned.
Yeah, they look pretty much the same, and that's exactly what the EBM is supposed to do. The EBM is designed to give you a simple formula that shows you what the edges of your graph are basically going to look like. It's not exact, it's a little bit off, but it's pretty close. Okay? But that's what the EBM does. Shows you what your graph would look like on the edges, but it's a simplified version. What it doesn't show you is what's happening in the middle. EBM has nothing to do with the middle at all. And the middle doesn't even look the same. But it's not supposed to. Okay. So any question on how we found the EBM there? Okay. Let's try the EBM of this one. What's the term that has the highest degree at the top? 2x to the fourth. And what's the term with the highest degree in the bottom? It doesn't have to be the first one, so make sure you look at all of them, just in case they didn't write it in the correct order. Yeah?
3x squared?
Yeah, it is the first one, 3x to the fourth. Okay, and now, what's going to happen with my x's there?
Cancel.
Right, they all cancel out, and what am I left with? 2/3. 2/3 is the EBM. Now, there was a second part to each of these questions. I didn't address that yet. It said, find the EBM, which I've now done, and any horizontal asymptotes. When we write a horizontal asymptote, it always starts out with what letter? Yeah.
Why?
Y. Y equals. Now, this is what the EBM is really used for. To find the horizontal asymptote, let's say it like this. Use the EBM. And let x approach infinity. That's how we're going to find the horizontal asymptote. So the advantage of doing it this way is you don't have to look at a really complicated expression anymore. We're going to be able to look at something that's much simpler, but would still give us the same horizontal asymptote as the original. So we found our EBM. Now let x approach infinity and tell me what happens to the EBM. As x approaches infinity, what happens to this part that I circled? It gets bigger. Right? If x is 1,000,000, then the bottom would be 3,000,000. If the bottom of the fraction starts to get huge and the top of the fraction stays the same, what happens to the whole fraction?
Get smaller.
It gets very small. And what does it approach? 0. Yes. So that's what the EBM is used for. The EBM finds the horizontal asymptote by doing this. So let's follow these directions again, and let's find the horizontal asymptote here. It says, use the EBM and let x approach. So what happens to this fraction as x starts to get bigger and bigger? There's no x. So then what happens to this fraction as x gets bigger and bigger? It stays the same. So the horizontal asymptote this time is 2/3. Those will be the two different things that could happen for today. you're either going to end up with an X in the bottom, and that's going to make your horizontal asymptote 0, or you won't end up with any X's, and then the horizontal asymptote is just that number. But there is an important difference between these two answers. On the right, that is an equation. On the left, that is just a number. When you write the EBM, it's okay to write it without an equal sign. In fact, it shouldn't have one. Okay, it's just a term. But an asymptote has to have an equal sign. An X equals or a Y equals. Depends if you're doing vertical or horizontal. So always write your asymptotes as equations. Yes, question?
Now, if you graph this, would it still show what the ends are supposed to look like?
Yes, if you graphed all of this, take a while to type all that in, but if you typed all of that in, and then you typed in this, and you don't look at the middle, but you just look at the edges, these two graphs would look identical. Yep. I mean, you might have to zoom out. Maybe you got to zoom out all the way to -50 and 50, or -100 and 100. But if you zoom out far enough, these two graphs will look identical. On the edges, not in the middle, just on the edges. All right. Any questions on how we found the EBM or used it to then get the horizontal? All right. So let's look at finishing up with a few sketches. The most important thing when you're sketching is to find all the asymptotes. If you can't find those, you're going to be stuck. Okay, so we got to find those. We're also only going to sketch problems today where the numerator is either equal to the degree of the denominator or smaller. So this would be a problem where the degree of the numerator is smaller. That's a 2, and that's a 3. This would be a problem where they're equal. They're both 4s. We're not going to do problems where the degree of the numerator is bigger than the denominator until tomorrow. Okay, so let's do this. So the first thing that we want to find are the vertical asymptotes. Sometimes they're easy to find. Sometimes, worst case, you're going to have to use quadratic formula. So we'll start with the vertical asymptotes. And then we're going to do what we just did in the last problem. Find the EBM and use that to get the horizontals. Once you've done steps 1 and 2, you're probably going to have something like this. A lot of these problems are going to have 2 verticals and 1 horizontal. So you're going to have your grid, your graph, kind of separated into 6 sections. We're going to end up drawing in like 3 pieces. Okay, so you'll see how it works. Once we get our asymptotes, then we need to check what's happening near the asymptote. Okay, so what do I mean by near? Well, let's say I had a vertical asymptote at 2. I would want you to go to the graphing calculator and plug in a number like 1.99. And then I'd want you to plug in a number like 2.001. Don't plug in 2, because that's the asymptote. Plug in numbers close to it and see what happens. And whatever's happening, we're going to put a dot on the graph to show what's happening. And then step 4, you're probably going to need a few more points. And we're going to use the calculator to help us get those. These aren't straight lines, so it's not like you can just get 2 points and then just be done. You're probably going to need like don't know, maybe 6, 7 points to get a good sketch. Because the graph is going to be in 3 separate pieces. And then step 5, you can always double check your answer with the graphing calculator. Okay, so I don't need a graphing calculator to do any of this, but it will make plugging points in faster because I'm going to use the table. But other than step 6, you don't have to have a graphing calculator. Yeah?
Is there a 5th step?
No. Forgot to change that. Okay, so we'll go through all those steps and try to make a sketch. Everybody have, so I can scroll down steps 1 through 5. Okay, that's what we want to sketch. All right, so step 1, find the vertical asymptotes. How do you find vertical asymptotes? Yep. Right, you factor the bottom and then set it equal to 0. This is factorable. Most of them will be factorable because if we have to start doing quadratic formula just to solve the bottom, I mean, this is just 1 step out of 5. So we don't want to spend 10 minutes just on this 1 step. So let's factor it. How does that factor? Yeah.
X minus 3, X plus 2.
X minus 3, X plus 2. Let's check it. X squared looks good to me. Yeah. So vertical asymptotes. There are 2 numbers you could plug in that would make the denominator 0. What are those 2 numbers? 3 and negative 2. Okay. I'm going to graph those 2 vertical asymptotes right now. So let's do 3 and negative 2. That's already broken my graph into 3 pieces. When you sketch, you always have something to the left, in the middle, and to the right. You can't cross the vertical asymptote, so it will be 3 separate pieces. Okay. What's the next thing that we find after the vertical asymptotes? EBM. Yep. Let's do the EBM. For the EBM, it's easier to go back to the original version, not the factored one. So you can get the highest degree term at the bottom quicker. What's the highest degree term in the top? X. Highest degree term in the bottom?
X squared.
X squared. And what does that give you EBM of when you reduce it? 1 over X. Okay. So now, what do we let X approach to be able to get my horizontal asymptote? Yep. Infinity. Yep. Let X approach infinity. What would happen to what's in this box if X approaches infinity? What would that fraction approach? Yep. 0. Yep. Because the bottom fraction would get huge. So we have a horizontal asymptote at 0. So that's the x-axis.
Why do we say X needs to approach infinity?
Because infinity is where the end of the function is, and that's what the end behavior model is useful for. Figuring out what happens at the very edges.
So if it ended at a certain spot, that would be but it doesn't.
Well, it never ends. It just goes on forever, like the axis.
If it did have an end, would it be whatever the end is?
You'll never have one that ends.
Okay.
These graphs are always going to go forever left and right. They'll never just like stop. Okay, so now the next step is check what's happening near each asymptote on the left side and the right side for both. The quickest way to do that is to make a table on the calculator. What would be a number that's a little bit smaller than 3 that I could plug in and see what's happening? When I say a little smaller, I mean within like 1/1000th smaller. Yeah, 2.999. Okay. I could plug in 2.999 by hand and do it all out. It's just going to take me a while. So the calculator can plug in repeated values over and over very fast. So let's do x squared minus x minus 6. Make sure we type everything in right. If we want, we can check our 2 vertical asymptotes to make sure we did them right. If you plug in 3, yep, get an error. -2, also get an error. So we know those are right. Let's plug in 2.999. That -4,000. So just before 3, what's my y value getting close to? -infinity. Yep. So just before the number 3, I am way down there. I know that's not -infinity, but that's the best we can do. Okay. What's a value that I could check that's just after this vertical asymptote? Just to the right.
3.001.
Yeah, 3.0001. Okay. If we plug in 3.00001, we're up at +4,000. So where do you think I'm going to be just to the right of that asymptote? Way up at +infinity. Okay, now let's do the same thing with -2. What's a number that's to the left of -2, but extremely close?
-2.111 or 0001.
-2.0001. It says -2 if you highlight it. It's not really -2. Just ran out of space. I'm at -6,000. Now let's check what happens when we cross the asymptote. Where do you think I'm going to be on the other side? Yeah, usually one side is low and the other side is high. So check a value extremely close. -1.99999. I'm at +6,000. Okay, so now we've got 4 points. That's good. Let's check a few more in the middle. Okay, this is step 4. Plot a few additional points. What would be some good x values to check that are in the middle?
1.
Yeah, 1. That's a good one. Okay, 1, 0. There's another point. What's another good point to check?
2.
You could check 2. So 2, we're at -1/4. And let's check 0. Check that one. 0, we're just a little bit above the origin. About right there. Okay, so I think I've got enough points I can do the middle section. We've got to stay as close to the vertical asymptote as we can, but we have to start to curve because we got to go through these dots, and we have to curve again to make sure we hit that one at the bottom. Okay, so there's our middle section. Let's check the left section. What would be some good x values to check that are to the left of that asymptote? Negative what? Yeah, you can do as many or as you want. -3, you're at -2/3. So right about there. What would be another good one? 4. 4? -4. Okay, -4, you're about -1/3. So maybe about right there. And then let's go all the way to the edge, -10. We're at -0.1. So just a little bit down. Okay, so I think we got enough points to see what's happening on the left. You stay very close. Start to curve. And come down just like that. And now let's check a few points to see what's happening over in this section. What would be a good x value to check over there? Yep, 4. We're at a half. 1, 2, 3, 4. We're at a half. And what would be another good one? 6, yeah, try to space them out a little bit. 6, we're even a little bit lower. That's like a fifth. Okay, so I think you got enough points we can see what's happening in the upper right. It's going to go through that point. Stay very close. Start to curve. And then continue to get closer and closer to that asymptote. Let's see how we did. So there's the left, there's the middle, and there's the right. Yeah, it's not perfect, but it's pretty good.
School.
What's that?
School.
Yeah. So that's generally what a graph with 2 vertical asymptotes looks like. 3 sections, kind of that S shape in the middle, and then like a curve in each corner. Yes.
Can it have more than 2?
Yeah, you could have a graph with as many verticals as you want. We never do any with more than 2. We'll do 1, or we could do 2.
Could it have multiple horizontal?
Multiple horizontals. There are some graphs that do. These ones I give you do not.
Could it have multiple vertical and horizontal at the same time or no?
I'd have to think about that a little bit and see. I mean, I guess it'd be possible. I think I'd have to find an example though. But off the top of my head, I can't think of one at the moment. Yeah. Definitely, if you had a piecewise function, which is really graphing 2 things at the same time, but they're different formulas, then you could do that. But I'm just trying to think of one formula that would do it all. I'd have to think about it. Okay. Good questions. Any other questions on that? All right, let's try one more of those, and then that'll be it. That one's pretty similar to the first one, so I'm not going to do that. This one's a little different because this time the degrees are equal rather than having the degree in the top smaller. But the sketch still looks almost identical. Okay, so we've got 3x squared plus x minus 4 divided by 2x squared minus 5x. Okay, and they're kind of giving us a hint this time. What do we have to do to the denominator to make the vertical asymptotes easy to find? Yep.
Factor.
Let's factor. This time, you can't do the fancier kind of factoring. All you can do is factor out an x. Okay. When you factor out an x, it gives us 2 values that would make the denominator 0. Anybody think they know one of them? Yep. 5 over 2, or yeah, 2. I'm just going to do it as 2.5 because that's easier for me to graph. So 2.5 is 1. Fill that in right here. You would get 0. And what about your other x value? Yep.
Is it
0.
0?
Let's graph those.
Why would the second one be 0?
Why would this one be 0?
Yeah.
Because if you fill in 0 here, you'd have 0 times 0 minus 5. And 0 times 0 minus 5 is 0. Yep. Yeah. You can find everything first if you want, and then graph later. I like to kind of graph it as I go a little bit. So 2.5. And what was the other one at? 0?
0.
Okay, so it's already setting up to be just like the other one. We're going to have our 3 sections. The horizontal asymptote, let's do the EDM. What's the highest degree term in the top? 3x squared. And what's the highest degree term in the bottom? 2x squared. What's your EBM? 3 over 2. And now the horizontal asymptote. Let x approach infinity in the EBM and tell me what happens to it. Yeah. Nothing. So your horizontal asymptote would be?
3 over 2.
And how would you write the whole thing?
Y equals 3 over 2.
Y equals. Yeah.
Would it be better to do 1.5 or 3 over 2?
You could do 1.5 if it's
Do you have a
easier.
preference?
No.
Okay.
No, maybe graphing 1.5 would be easier because you can think of the decimal. But I'd accept either one. So 1.5. Okay. Now we just plot a bunch of points. And the table is what's going to make that pretty fast to do. So we've got 3x squared plus x minus 4 and 2x squared minus 5x. Okay, if you want to get rid of your old values, you can. You can keep them. It doesn't really matter. Okay.
How do you get to the table?
Second and then graph.
Second graph.
Yeah, second graph. Okay, let's start with our asymptote at 0. What's a value that's just a little bit smaller than 0? A little bit smaller than 0.
0.9999. Alright. 0.0001.
Okay, that's a little bit bigger. We can check that too. We do need to do that, but what's smaller?
Negative 0.0.
Yeah, negative 0.0001. It's a little bit smaller. Let me make sure I typed everything. I must have typed something in wrong. 2x squared minus, oh, I didn't put divided by. I knew when that happened we didn't get what I was expecting. There you go. So when you plug that in, just to the left of 0, we are down at negative 8,000. Way down there. What's a value a little bigger than 0? 0.0001. And when we plug that in, we're way up at positive 8,000. Caleb, what would be a value a little smaller than this second asymptote?
2.
Let's try to be within like 1,000th of it.
Okay.
Really close.
It's like 0.49.
Yeah, so that's 2.5, so let's do like 2.499. And we are way down at negative 35,000. And then let's check a value a little bigger, 2.5001. We didn't check 2.5 itself, but if you do type it in, you get an error, which that should happen. And this one is up at 345,000. What would be a good value to check in the middle? 1 and 0. So 1, when you plug in 1, oh, we can't do 0, that's an asymptote. But 1, 0 we can do.
You can do 2.
Yeah, we could do 2. 2, negative 5. This one's very steep in the middle. So it's going to kind of curve down. Just a little bit of a curve. And keep going. What would be some values to the left? Let's pick 2 values.
-2 and
Negative 2, negative 10. So 1/3 and 1.1. So 1/3 and 1.1. Okay, got enough on the left that I can see what's happening. Oops. Make sure you don't cross that vertical. And how about some values on the right? 3 and 7. So 3, we're at about 8.5. 3. So right up about there. And then what was the other one we did? 7. Just above 2. 1, 2, about right there. Okay, so in the upper right, it's got another curve. Kind of like that. Now, because it's so steep in the middle, the calculator is probably not going to draw this one correctly. And still likes that graph. It really didn't. It almost looks like it just kind of stops. This on the calculator is not what it should look like. It should look like what we do. Any questions on that one? Once you get your asymptotes, it's really just using the calculator to get a whole table of points. So that's the homework for tonight, page 234. We'll look at that tomorrow, and then the goal is to finish up everything tomorrow, have a review day Thursday. If we don't finish tomorrow, well, we'll finish a little on Thursday.
Did you want the extra?
Yes, if you have the extra credit, I will take that.